progress.
Yeah. This is probably good for you then, this little chill in the air and all that. Just like walk around. Yeah.
I like good.
Me too. Me too. I almost wore one today, but I forgot.
I was like, I want to keep wearing some shirts.
That's my son. My son is, he wears hoodies like year round. Can y'all hear me on Zoom?
Yes, we can hear you.
Yes, we can hear you.
Yeah, the audio may be a little bit, let me turn it up, see if I can turn the mic up. The audio may be a little bit different because I'm not like standing right in front of the laptop. But I'll try to project my voice like I used to before COVID. So let me, I'm gonna share my screen and then we're gonna get started. Chicago, Huntsville, Douglasville. What is it all? How y'all say? Either way. Oh. Over here. Kind of cool. So this is all that's coming in person. We can keep doing this. Okay, yeah. What I'm gonna do though, I'm gonna move the podium so I can be closer to the computer. Or I can move the computer so it's close to the All right, for those on Zoom, if you at any moment you can't hear me, just say something, and I'll try to speak up or I'll move closer. So turn the camera on. Yes, y'all see my profile. What position do you play, Chase?
Middle hitter.
She's 7. But she's short. Keep telling her to work on her vertical. Calf raises, box jumps. She won't listen. Everywhere. Can y'all see that? Is that enough for y'all here? Magnify that some. Resolution is bad. But you do have it in front of you, all right? All right. So we left off talking about pKa, and we were talking about acidity and proton transfer, and today we're going to pick up where we left off. I think the last question answered was number 4, asking about the conjugate base of the weaker acid. And we said that that conjugate base is less stable, right? That's the whole idea behind pKa, is that the proton leaves more readily if what's left behind is more stabilized, right? So the conjugate base is more stable, pKa is going to be lower. Conjugate base is less stable, the pKa is going to be higher. So we're going to work, I want to work through this example here on number 5. Let me zoom in for the people here. You can just get it, write it down if you need to. So HA, we'll put it on the board too. And then I'll write it down for the people. If I know how to teach it practice. Can't even find a dry erase marker. So HA has a pKa of 15. That's given. And then HB, let me not write it like that. As a pKa of 5. So these are my 2 acids, right? And it says it asks us to draw the equilibrium that will result from mixing HB with NaA, right? So this is acid base, Na plus A minus, right? If you see what's happening here, it's going to be so it's going to be H plus Na, so that's negative. So it's positive, right? So what happens between these two? If this is my acid, this is my base, and there's equilibrium between them. All right, how do I show the proton transfer between NaA, which is the base? Don't worry about sodium, right? It doesn't participate. The only thing that's going to participate is something inorganic, is something that has electrons. Doesn't have electrons, not going to react, right? So how do I show that? I'll write it this way, so we don't have to fiddle around with the arrow. What is that proton transfer going to look like? Anybody? So this is the base, and it's always so the base is going to accept H plus. Is that right?
Yes.
So the base H plus accept H plus. How do we show that? There's a mechanism for that. Is that right? Isn't that what we say the mechanism is? Detailed description of a reaction using curved arrows. Is that right?
So with draw a curve, because we say you always draw a curve arrow from electron density.
Yes.
So would you draw a curve arrow from like boom, like A,
Yes.
and then to the H?
From here to here. Is that right?
Yes.
I'm going to draw the arrow. Let me rewrite this for all it's going to look like this. I'm just going to put the H out front. So the arrow is going from here. Is that right? So then on the other side of the arrow, what's the conjugate acid going to look like? Remember, the conjugate acid is the base after it picks up H plus. Okay, so that's I like that because the sodium is associated with the base, but remember it doesn't have any electrons. So the HA. Is that right? Because this is where your bond is being formed right here. Is that right?
Correct.
So on the other side, it's going to be, I'll write it down here, HA plus what?
B minus.
B minus, excellent. Because I do have to break that bond back to B. And then this is Na plus. Anybody not following that? So it's going to be on this side, HA plus B minus. So you here now, because this is an electrostatic attraction. Or what we call it when we're looking at intermolecular forces, ionic bond. But it's not really a bond. All right, questions about that? So this is going to help us answer the other part of that question. Because the other part of the question is, now, how do we predict equilibrium? Because it asks to predict which side will be favored. So we put the arrows in, we got the mechanism. Which side is going to be favored? What is the pKa of the conjugate acid, which is HA, right? We were given that at the very beginning. It's 15, and then HB. Five. Is that right?
Right.
Am I moving too fast?
No,
Everybody
no.
good? All right. On Zoom, everybody okay? Can y'all hear me okay?
Yes.
Yes, we can.
Okay, great. All right. So how do we predict equilibrium? What's the rule?
So weaker acid is
Always.
so
Weaker acid is always favored. Go ahead.
higher pKa.
Yes. So the acid is here, the conjugate acid is here. Right? But equilibrium always favors the weaker acid. Is that right? So for this, the pKa is 15. Here the pKa is 5, but we put that on a fulcrum. Right? We can say that equilibrium is going to favor products. Right, so this acid has a pKa of 15. This acid has a pKa of 5 based on the information up here. HA is 15, HB 5. Equilibrium for favorite products. Right? Equilibrium is one of favorite products. That's how the way that we predict acid-base equilibrium is based on pKa, the pKa of the acid and the conjugate acid. All right, somebody explain, whether you're on Zoom, you can chime in, or if you're here. How many times more acidic is HB than HA? Gotta move this little mechanism definition right here. So 10 to the 10. Oh, let me move this. I'll clean this up later. So we're asking that, what we're saying is that it is what? X, which is the number of times more acidic, is 10 to the what? Delta pKa, right? Is that right? So that's 10 to the 10th. 15 minus 5, 10 to the 10th. All right, are y'all following that on Zoom? We said that HB, we should have to go through all the steps at this point. It's 10 to the 10th times more acidic than HA. All right, 10 to the 10th. What is that? A billion, or is that 10 billion?
I think that's
15
a
times
billion.
more acidic. Yes. So again, let's talk about water equilibrium is going to favor the products. For every 1 H that HA gives up, how many H's is HB giving up to go forward? 10 billion. See that? No, I see your face. See, this is different from Zoom. I can get the reactions, then I can probe a little deeper. Are you following? So if Michael is HA, and Michael is over here, and he's here, here's one. And you're HB, you over there like this the whole time. You understand what I'm saying? So every time he gives up 1, you're giving up 10 billion. So the reaction is going this way so fast and coming back so slow that the product has to be fair. If that makes sense. All right, that's the point I've been trying to make with this. That's why it's important to understand how to calculate how much more acidic one acid is than the other, because then it puts into perspective what's happening in equilibrium. If it's going forward faster than it's coming backwards, then the forward reaction is going to be favorable. You good on that? All right, we good on that on Zoom? I feel like I'm teaching the class twice, but it's good though. This is exciting. And we still got 26 people logged in, so that's good. All right. Let's move.
I have a question.
Section. We're gonna start knocking out some of these problems up here. Let's start on, let's go to 146. We're gonna work through those. I gotta erase this if y'all like with that. All right. All right. That's horrible. Do you have this handout? Do you need it? No. This is bad. You sure? All right. Yeah. Cause it's bad, it looks fine on the screen, but it looks bad here. Cause it's the projector, it's too bright. Let's see if I can make it more, increase the resolution a little bit. That's all right, I can zoom in. All right, we're gonna start with A. That's like a warm up. I'm gonna put these on a different sheet so we'll have room to work. We're gonna go through the mechanism and we're gonna talk about predicted equilibrium. We're gonna look at pKa's up, all that stuff. So let's do that. So let me just copy this and put it on another page. All right, we're gonna take A. A is H2SO4, so it's sulfuric acid. We'll write it out. Now that's CH3COO minus. That is the acetate anion. So this actually is it's the conjugate base of acetic acid. So it looks like that. So I'm gonna actually write this out. I want you to see these functional groups and all that glory. So this is CH3COO minus. And then when you have a functional group like this, actually this is a great example. You can do everything. You can do hires and everything with this. All right, so this is the acetate and sulfuric acid. I'm really kind of big on nomenclature because I can remember as a grad student, I kind of struggle with that part, knowing what the names and stuff, you know, knowing the names and knowing the proper way to call stuff out. But that's very important. If you can't speak the language, you're stuck, right? You go to China, you don't speak Chinese and you don't have a translator, how you gonna talk? So speaking the language of chemistry is very important. So yeah, so this is my, which one do you think is the acid? Let me ask that question. Okay, good. I meant to say base, by the way, but you got me. So this is my acid. By default, this is the base. Is that right? By default. All right. Now let's go through the mechanism of proton transfer. If this is my acid, this is the acidic proton right here. That's very important. Right? Your acidic proton, we can't really see the highlight. Your acidic proton is always going to be attached to a highly electronegative atom. Right? That's really important to be able to identify that. Because once you find out what the acid is, then the base is by default. Right? You don't have to work, they have to guess about that. All right. Now let's put in some arrows. So what we're going to do with this one example, we're going to predict equilibrium. We're going to do the mechanism, and we're going to compare the acids and see why the stronger acid is the stronger acid, while the weaker acid is the weaker acid. We're going to do that. All right. So what would the arrows look like for proton transfer? Somebody want to come up? This is the beauty of coming in person. Before COVID, people would be at the board the whole class, just working. So what would you do here? Right, we're talking about this proton transfer from the acid to the base.
From the acid to the base.
Mm-hmm.
Okay. Okay.
Are you good?
And we're still drawing the arrows from the
Same.
electron.
Always. Never deviates. I don't care how it's written, how it's twisted up. You always go from the base to the proton. Good. And you break that, give it back to oxygen.
Or
put it on the atom.
On the atom.
Yeah. That's important, right? and I'm not calling you out, but just bear with me. If Kadir had put that arrow here, what would that have meant?
Double bond.
That pair of electrons is making a double bond, and it is not, right?
It's not.
So you want to put it on the atom, from the bond to the atom. That's very important. All right, don't go anywhere. I'm gonna come back to that. So over here, if you're on Zoom, Kadir put the arrows in like this, and like that, right? So that pair of electrons between the OH bond went to, look at that. Right back where it was. Perfect location, right? So now, what does the conjugate acid and the conjugate base look like on the other side of the arrow? Okay. Okay. Good, excellent. You good? Good. I'm right here. This is the conjugate acid. It picked up that proton from the base. Well, it picked up the proton from the acid, and this is the conjugate base because it gave up. It was the acid that gave up the proton on the reactant side. This is acid, base, conjugate acid, conjugate. All right, excellent. Now, which way is the equilibrium gonna favor? We don't know.
Yeah.
We can approximate. Can we approximate using hires?
Yeah, we can.
If we use hires, we can approximate, right? But we don't know the actual numbers. So if you look at the two conjugate bases, right? Well, the conjugate base and the base, that's what we're looking at to approximate using hires.
I think it would be this. This will be the more stable base.
Okay. Why?
Because if you're looking at they're the same atom, right?
Mhm.
But
So
this is
same
this
hybridization.
is the induction electronegativity.
Okay, what else though?
And then resonance too, right?
You can do resonance more than once
More than once. You can do it.
compared to the other. Now let's prove that. Look up, somebody Google the pKa of sulfuric acid. That 10G back there. So -10. Is that good or bad? That's a really good acid, isn't it? And then somebody Google acetic acid. It's 4 point. I don't want to give it away because I asked you to look it up. So the pKa, now we're going to determine the equilibrium. The pKa of sulfuric acid is -10. pKa of acetic acid is 4.76. 4.76. Good work, Kadir. Thank you, sir. Everybody got this down? So I can kind of, because it's out of place now. All right, pKa of sulfuric acid. So which one is the better acid? Sulfuric acid. How many times more acidic is sulfuric acid than acetic acid? You can round up to 5, yeah, that's fine. 10 to the 15 times more acidic. That's a lot. What is that? Is that a quintillion? That's quintillion. It's trillion. 12. That's quadrillion. Quadrillion. That's a lot. So we can say that sulfuric acid 10 to the 15 times more acidic. 10 to the 15 times more acidic. That's all. It's a huge difference. All right. What can we say about the equilibrium then? Everybody got this part down right? It's going to favor the product, isn't it? Equilibrium is going to be always going to favor the weaker acid. So when I write equilibrium arrow, they'll look like this. But the product is favored over the reactants. Is that right? Anybody not following, whether you logged in or whether you're in person? Everybody still afloat? You need a light?
I have a question.
Go ahead.
You said that it'll favor the product, but
Yeah.
it doesn't the sulfuric acid have, isn't it more acidic?
It is. And that's why. The reason it's going to
Oh,
favor
okay.
the right is because it's 10 to the 15 times more acidic than acetic acid. So every time you're going this way, a quadrillion times versus coming back the other way one time. You follow?
Yes.
So yeah, so the more acidic acid being in the starting material is going to favor the product because the product
Okay.
is a weaker acid and it's not going to give up its proton as rapidly as the starting material.
Okay, got it. Thank
So
you.
even though they go back and forth because it's equilibrium, the equilibrium is going to favor the right side.
Okay. So the equilibrium is going to favor the right side because it's weaker.
That's right.
Okay.
Equilibrium
Thank you.
always favors the weaker acid. All right, now let's talk about the two acids, right? Sulfuric acid and acetic acid. Right? And one of them has a pKa of -10, and this has a pKa of 4.76. We already talked about that. Why do you think sulfuric acid? You mentioned it, but I want to dig back into it because this is the kind of discussion you can have on any of these questions. If you got the acid-base reaction, you can answer how many times more acidic one is than the other. You can answer which way the equilibrium is going, and you can answer why one acid is a better acid than the other. Right? Based on what we know about pyrites, is that right? We can use that to answer this question. So when you're using pyrites, what you compare are the conjugate bases. Is that right? So now let me make another page for y'all. So now what we're doing now is we're going to compare two acids. And to do that, and to do the comparison using hierarchy, you just look at the conjugate basis. All right. So hierarchy is what? Hybridization, induction, resonance, electronegativity, and size. Is that right? What can we rule out right away? Hybridization, because both acids, the charge is on oxygen, right? And oxygen is sp3 hybridized in both cases. Is that right? All right. So we can rule out hybridization. We can also rule out size and electronegativity, can't we? Because since it's on the same atom, they're the same size and they have the same electronegativity. All right, so now we have induction and resonance. And I know, Kadir, you mentioned that the OH would be inductive because of its, because of the electronegativity. But it's actually a good donor. It's a good donor too. So the induction part, maybe from here, from the sulfonate part, that may give you some induction, but it's really going to come down to how many resonance forms each one has, right? So we'll rule out induction, electronegativity, and size, and we'll say that this can do resonance here and here, or it can do it here and there. Is that right? So you can really draw two resonance forms for that. All right, if y'all following along our line, we can do resonance here and here, or we can do it or here. All right, so this has multiple resonance forms. What's all about? Yes. All right. So you got multiple resonance forms for the conjugate base of sulfuric acid, and then you only have one resonance form for acetic acid. Right, so the stability of the conjugate base in this case is coming from those multiple resonance forms. So now that is how we explain this observation. And we can say that this is stabilized by multiple resonance forms. Right. Make sense? Anytime we're comparing acids, we're not looking at the proton, we're looking at the conjugate base and determining from the conjugate base whether it's stabilized by one of these 5 factors: hybridization, induction, resonance, size, or electronegativity. Everybody good? Everybody good online?
Yes.
Yes, sir.
Any questions about anything? Let's do another example. We're still working off of problem 1.46. Which one? I'm gonna let y'all pick. Pick one. You don't have it. So you got it, Mike. Pick one. Reagan had it too. So the two Georgiaites, y'all gotta pick. Don't pick Herschel Walker. I mean, excuse me, no mind. D. That's a good one. So Michael picked D. We're gonna do D. All right, I'm gonna put another page in so we can write it out. We're gonna do all the same thing we just did here. Predict equilibrium, find the pKa's, and determine why one acid is better than the other, all that stuff. All right, so D. All right, I'm gonna write this out. So it is a y'all can see that here. I think I'm just gonna leave this one on. I'm just gonna work through this one on the screen. We're about trying to line arrows up. All right, so this hydroxyl group is typically a very good base. So when you see that OH minus, whether it's by itself or with a counter ion like potassium or sodium or whatever, you can automatically say that this is going to be the base. It's automatic. Our base. And it's this. I'm going to give you a name, trimethyl. It's trimethyl because it has 3 CH3 groups attached to it. Ammonia. The IUM at the end indicates that it's a cation, so it has a positive charge. That's why it's called an ammonium ion. Ammonium. Right. So this is the OH minus is my base. This is my acid. Is that right? So let's go through the proton transfer mechanism. Always the same two arrows from the base to the proton, and from the bond between the proton and the atom is bonded to back to that atom. Always the same arrows, both here like that. Here. Back to the atom. Never changes. See, it's on any exam. MCAT, DAC, PCAT, whatever. Never changes. The arrow never changes. Always base the proton, and then you break the proton bond catalytically and give it back to whatever atom that proton is bonded to. That never changes. Right? What is that? What's the conjugate acid? You sure? It's fast, man. Don't be shy. What's the conjugate acid look like? Or you can like cross it up. I was about to write that over there. With my fingers. It's H2O, yeah? HOH. This is conjugate acid. It's this proton right here. That got picked up. Yeah. Y'all see that blue? It's not showing up on the, it's showing up on my screen and on the laptop, but not on this screen. Proton that got picked up out of OH. All right, and then what's the conjugate base?
It's gonna be, yeah, it's gonna shine up, and it's got a long pair by the end.
Here. All right. Well, this is not methyl. Amine. That's a amine functional group. It's a nitrogen with either carbon substituents or hydrogen attached to it. All right, so trimethylamine. So that's my conjugate base. Somebody look up the pKa for water. You can do it online or you can do it here. Doesn't matter. pKa for water, and then somebody look up the pKa for the trimethyl ammonium ion. That's 6G power. What y'all on now? 10G.
Right.
14. We'll take it. So this has a pKa. What about the ammonium? Anybody got it? Do I need to look it up? Don't let me beat you. Anybody online got it? Any chance? Spike? Is that 9.8? Good. Yeah, we'll leave it at 9.8. You can round it up, but normally pKa numbers are very precise. So we'll leave it at 9.8. Now, when you want to calculate the difference,
Yeah.
you can round it up that there. I was about to squeeze that. All right, so we got 9.8 pKa for the trimethyl ammonium salt or the trimethyl ammonium ion and 14 for water. Which way is the equilibrium going?
Towards the 9.8, so it's gonna take
Start with here. You sure? This is 9.8. That's 14. Which one is weaker? Higher the pKa, the weaker the acid. The lower the pKa, the stronger the acid. So the water is the weaker acid. That's okay. Now, when you see that again, guess what? You won't miss it. So it's here. Equilibrium is going this way. Right? Because the weaker acid is water. Is that right? Anybody online now see that?
Yes, okay, so it's favoring,
The weaker
No.
acid?
yes, it's favoring the weaker acid, so that would be on the right side?
Yeah. So it's
Oh, that's-
favoring the product.
Okay,
But
yes,
remember, whenever we write any reaction, it's always reactants to products. We put reactants on the left, products on the right. So it's going to favor the products.
okay, yes, because water has the lower pKa, so that means that it's higher,
So, no,
has higher.
actually, the pKa is 14 and the pKa of the other acid is 9.8. So it has a higher pKa.
I mean, it has a higher pKa, okay,
Yeah, so lower acidity. If that makes sense. Are you following that?
yes, I am.
Okay, all right, just making sure we're all on the same page. Okay, how many more times or how many times more acidic is the trimethyl ammonium than water? 10 to the 4th, right, or 10,000, is that right? Write that down, trimethyl ammonium. 10 to the 4th time more. More acidic. Equilibrium is going to favor the products. Right? Now, we're going to ask this last question because we only got 3 minutes left. Why is this a better acid than water? What are we looking at? Looking at the conjugate base. So let's compare the conjugate bases. Conjugate base for trimethyl ammonium, trimethylamine. Everybody following that? I'm not going through the whole spiel like I did in the last example. When we compare the conjugate bases, what we're looking at is why one conjugate base is more stable than the other, which explains why one is more acidic than the other. So that's the conjugate base for that. And then the conjugate base for water is here. And it's made.
You still have CH3 on the head?
Yeah.
Oh, you use those stones.
That's good. I'll write them off. But if you thought that, somebody else is thinking too. All right, so we want to answer that question. We're going to stop here. We'll answer it on Friday. Because it's counterintuitive. Oxygen is more electronegative than nitrogen.
I was gonna say it's probably because since oxygen is more electronegative,
But that would be good, right?
but wouldn't that make it more stable?
It should. It should, but this example when you compare nitrogen and oxygen, it's kind of counterintuitive.
Okay, yeah, all right.
It's got a little something to do with the atomic radius. it's a little bit, nitrogen is actually a little larger in atomic radius than oxygen. But we'll talk about it Friday. All right. Thank y'all for staying tuned in, and we'll see you on Friday.
Thank you, Dr.
Professor,
Russell. Have a nice day.
Okay,
Professor, I have one question.
go ahead.
Oh, is that me? Or is someone else asking me a question?
No, go ahead.
Okay, I'll go ahead. So in problem A,